Okay, I'm not sure what's happening, but the live stream is not working, but the recording is working. So I'm going to record it, and then if there's um, then we'll post it because I don't want to waste more time on this. Um, okay. Okay. So today we're going to be going through the latest results from Anthropic, where they extend their circuit tracing apparatus to include attention as well. Um, this was one of the, let's say, their biggest, at the end of their post, they mentioned that the biggest problem with their current attribution graph setup was that because it froze attention, you couldn't really understand why certain attention patterns were like they were, and although you did trace the influence through that attention pattern, um, they argued that it's important to understand the QK the KQ circuits as well as the information through MLPs to actually be able to understand the circuits. And they, in fact, in the post, I'm pretty sure, either in the post or in this post that we are reading now, show some examples where if you don't actually trace through attention, you get you don't get that much information. Um, I hope that most people are aware of 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 their previous setup. Their idea was that they replaced MLPs with what they called cross-layer transcoders, and in this work, they're um, they're doing, as I said, QK attribution, where they, I guess, they describe attention at scores as bilinear functions of feature activations from queries and keys positions. And in particular, they look at these three. Let me see if I can put everything. Yeah, they look at these three kind of problems that were not or hypotheses that they talked about, but they couldn't previously look at because they didn't have any kind of attention. So they look at induction, which is attention-mediated phenomena. They look at these opposite words, and they look at these multiple question interactions where you have to look to know that there's multiple questions, and then let's say pay attention to the correct answer. And they say they found new kind of mechanisms like these heads, concordance discordance heads, that attention circuits have used many heuristics, even in simple contexts. For instance, in the multiple choice prompt, the mechanism to find the correct answer also is complemented by a mechanism about attending any of the answers. And I'm going to start going on. Yeah, so this is what I was kind of saying. The reason why attention attribution is important is that, yeah, transformers the MLP writes in the same token position, but if information is carried between tokens, the CLT abstraction, the replacement models that they trained didn't really capture that well, and so all the attention information was being passed through, but they weren't really interpreting it, and so it was not clear which edges were the most important for a given edge. And also they didn't explain why each edge contributed the amount that it contributed to the attribution graph. And so what they do here is that they're going to be trying to explain the attention pattern of each edge. And to do that, they decompose the residual stream as a sum of features, as a dot product between feature pairs. And this is going to be explained later. There's a breakdown. And then they also want to explain how attention heads participate in the graph. So not only how much, how is the specific pattern formed, but also the specific contribution that each head adds to the attribution graph. Yeah, which basically, if you remember the previous work, before there was just a single connection between each edge, between each feature and each other feature, even if they were mediated by attention. And I guess here they're saying that they're splitting these edges depending on the attention edge, which I guess makes the graphs a bit more complicated, but let's see how they do it. So this is the equation that they're saying that they can. This is the attention score that you normally get between keys and queries activations, and that you can separate it into multiple terms. I guess so. This is just expanding this into the let's say the SAE shape. So you have a bias, an error, and then the sum of the features that are active. This is the activation, and this is the vector, and the same on the other side, but one with the queries and one the keys. And they say that you can even separate this a bit further, where you just have feature interactions. So features interacting with features, then features interacting with the errors, the keys and the query, the bias terms, the biases with the errors. Then they say to ignore this, which is constant, and then this error interaction. So there's multiple. So this is error, bias, and then the W matrix, bias and the query, and where is the bias and the features, and then this is features, and this is features and errors. And the sum of all these terms, you can make the score. And I guess if you're trying to trace through, you only need to take into account. You can drop kinda the constant terms. Well, you can drop the constant terms, but for instance, here these errors are not really constant. I don't know how they deal with them, but they'll probably explain it a bit below. But basically, instead of just freezing the attention as they did before, they're now really writing attention as a combination of features. And I guess they're going to discuss how to train what models they exactly trained for to get these features in this expression. Did I capture this well enough? I think. Let me see. Yeah. Yeah, this is kind of something that's not that important once we complete it. So so before attention, they have the residual stream. They train an SAE on the residual stream. They get the features that are active. And then this this matrix here is just all features interacting with all features. I guess, yeah. And you see that the different scores that they get for the attribution. So the different scores here. I guess that's what's here. Yeah. The passage vectors to keep here and both of them together. Yeah, which is this thing. And then they basically have query features and key features, and they see which ones are the ones that matter the most. So you see that there's this query feature, which is aunt or uncle, and then this key feature, which is male first name, which has a high score. And this is like one of these different squares in this matrix. But this, and maybe someone that has read this can also chime in. I don't understand if these features are going to be from token position. It's from yeah. So this is a single at the attention of one token to another token. A single, like all these query features are the features at the current token, and all these key features are the features of the token that this token is attending to. So you will have a bunch of each of these represents a single in the attention graph. It represents a single square of the attention graph. So you'll have a bunch of these squares for each position on the attention pattern. Which seems a lot of information to look through manually. So I wonder what they do to deal with this. Yeah, this is an interesting point. So here you only have a single square, like in the attention. Sorry, attention transformer. I wanted like attention. Yeah. So this matrix here only accounts for a single of these squares. The thing is that to get the real attention pattern, you do softmax over all the indices, right? And so you kind of normalize attention, And this means that you don't know if these magnitudes are going to be the real magnitudes of impact at the end, because you need to do all other keys to actually be able to get the row of the attention pattern. Um, yeah, you need to do a bit more than just this. Um, was this part kind of clear? I think are there like specific questions about this part that people have, like some comments? I'm just going to be checking the chat because I cannot see there's people in the chat. Okay. Yeah, if people are writing in the chat, I cannot see the chat because I only have one screen. So yeah, this is how they started to do attention pattern decomposition, and they can kind of see how features interact between themselves. But they say that this is not the full story, and actually they wanted to do the second part, right, which is to after getting the the attention pattern, understand how these features interact between them. Yeah, they this is an interesting point that they raise. They say that if you just used features like they do in the CLT, there's the features of the transcoder, the paths grow a lot. There's a lot of different paths that a feature can take, and because of this, yeah, it would be very. You'd have to do a lot of computation to keep track of all the possible contributions. And so instead of doing that, they do checkpointing, and checkpointing means yeah, they talk about three different strategies. Let's look at the picture here. So this is what would happen if you don't do any kind of checkpointing. You see that each layer you can do a lot of different paths. So you can do all these paths to reach to this point, because you can either just let's say go to stay in the same token and only move at the last time, or you can go to the next token and stay in the second one, and etc. So you have a lot of paths as you go through the layers, but by checkpointing you can kind of reset each layer, by saying, okay, instead of keeping track of how this feature goes through the different layers, I only keep track of how these features goes to this layer, and then here I check all the features that exist on this layer, and I keep track for the next layer, and you just do this kind of checkpointing, and this is what they talk about with residual stream SAEs. Or you can do these MTCs, so multi-token transcoders, where instead of having normal attention, you do a transcoder on the attention, and so in that case it's a different kind of checkpointing. You checkpoint it in a different way, because now this tells you information about every token position, right? Yeah, because now, sorry, not yeah, this limits the number of features in the path, and so you can bottleneck it through MCTs. I don't know what these attention out SAEs are. I guess they're just SAEs trained in the output of attention, which do the same thing as the residual stream SAEs, but are checkpointing stuff on a different way. So you just trace your feature through attention until an attention out SAE, and then from here it's kind of resetted, and you don't have to think about all the exponential like growing paths, because now you just keep the paths that are most important coming out of this attention out SAE. They say that in this post they adopted the residual stream SAEs. Because the other ones accumulate error, which is very important when doing attribution graphs. And then this is what they were doing already, right? Yeah. So now you'd have to do, let's say, interactions between features where you have features at the source position and features at the target position, and you'd be already doing something similar to this for normal attribution in graphs, but now you have they say that they're keeping track of stuff to be able to look at different ad contributions. And now they talk about an example. I wonder if people have questions in this thing. I'm unfortunately I cannot really delve too much into these multi-token transcoders because I just skimmed through them, but it's good that they actually end up not using them for this post, and they just train SAEs. But their SAEs are also special. They're basically transcoders, but on the residual stream, right? So they read from the residual stream, and then they try to compute all the next layers. It's like a cross-layer transcoder, but in the residual stream, but it's basically the same thing. Okay. So I see. So here they talk through an example, and hopefully the example is going to be helpful. None of this is interactive. I kind of wanted. Nothing is interactive. Okay, so we have to follow it step by step. So here, this is the example of an induction task where IQ has to complete Sally after ant. I'm bad at saying this word. And the way that we think models do this, or that there's some evidence in the literature that they do this, is that they will have some special attention heads that would be attending to that at this position aunt would be seeing that there exists this aunt here, and so they would copy the induction circuit would copy the next word, which is Sally, and this should be the output. Uh, and so this is what they're going to be trying to investigate. So how does the model? We know that this kind of exists, but uh, they're trying to answer how does the model decide to transport this token to this position, uh, and how does the information from Ant get passed through Sally, and um, without doing this kind of attribution, the attention attribution, we wouldn't be able to answer this kind of um, answers. Um, sorry, I kind of was expecting that this had more interactive graphs, um, but it looks. Am I missing something? Do they not have? Yeah, they don't have any. Okay, they only have print screens. Okay, so basically they do the normal um, attribution graph stuff where they're trying to see what are the features that make the model say Sally, which is the, let's say, the correct answer. And the way that they do this is that they just trace from that node now to the 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 the, the second. So they're doing this kind of tracing, like what features influence here, but because they're doing attention, they can see that there's some influence that comes from this Sally token, um, and that it's mediated by a small set of attention heads. That these attention heads are are doing this interaction between saying aunt or uncle or other families on the query side. So the side of the attention that's looking. So in this case, this is the query. And then on the key side, it's features that say names, uh, or features that say this is the name, specifically say this is the name of an ant. And so to give some examples, they show here that these are the keys. So you see these features activate on the names of aunts and uncles or on generic names, while the queries activate on aunts or some, well, these are exactly the same. I guess this is probably a mistake because they're saying something else. But yeah, this kind of interaction between ant features and say a name of the ant features was not quite seen on the previous attribution work, and so it's interesting that now they're able to show that the attention is doing this kind of connection between, okay, I saw the token and I need to say now a name, which now they represent it in this way. So I saw ant. I need to say that the name of the ant, and the name of the ant is Sally, and so I say Sally. And then they to validate this kind of circuit, what they did was that they selected the heads that had the most contribution and removed and removed the feature name of aunt uncle, which makes the model go from saying Sally to saying Margaret. So I don't understand this. I was expecting that if you intervened on Sally, this would happen. But they're saying that they're intervening on saying the name of an aunt. Does anyone have an idea on what's happening here? Like it, I would expect that if you intervene here, why would the model not say Sally still? Why would it say a random?
I think the feature is not like say the name of an aunt or uncle. It's like a feature labeling Sally as like this position marks the name of an aunt or uncle. So it's as if maybe
Right.
it's as if the context didn't say Aunt Sally, it just said like Sally almost.
Right. It's just it's as if the model forgot that there's a signifier here, and it just sees aunt here, and so it just makes a new name instead of understanding that this was already referenced. Is that your idea?
Yeah, I think so.
Yeah. So I guess yeah. So that's what they're saying. They're saying that they're transforming Sally to say Sally, uh, and if if they remove this, the model no longer wants to say Sally because now it's kind of like it doesn't associate Sally with aunt. Um, and here instead they're trying to see how they move to the Sally token. This is the name of an aunt. Um, which for me it's not as obvious if that this is what's happening. Like these two questions seem I don't quite understand why they're separate. Um,
Wait, so is this one the one that like this is trying to figure out why the aunt or uncle feature lights up on the second time Sally is, or no, not even the first time.
no. So this is just trying to understand. They're claiming that there's this information, this kind of meaning of this is the name of an aunt is copied to the Sally token, to the first Sally token. Um, and that this is kind of a different mechanism, I guess, from this one, which says that if you see Sally, you should say Sally on the second and token. Because they're saying it's kind of a two-step process where they first say, okay, when you have and, you're copying from the token Sally something, and the token Sally is saying say Sally. But for the token Sally to say Sally, the it must know that Sally is the name of an aunt, and so this is this kind of step here where they're trying to see how the fact that Sally is an aunt gets copied to Sally. Um, and so they say some features that activate on like titles and on aunt, and then some features that activate on first names and of names of aunt of aunts and uncles. Um, and they don't have any example like they did before, but they say that the interactions between these features is what makes the model say um, know that Sally is the name of an aunt, but they don't do any kind of uh, attribution, like any kind of ablation in this case. Um, so yeah, they just say that they think that this is what's happening, but they don't really show. Um, they don't really show any evidence. I mean, they don't do any experiment to show that except just observation. Um, and these two things, this induction head and this previous token head, are kind of heads that were already, let's say, observed in the wild and are part of these induction circuits. But yeah, here, at least on this example, I don't know if the next examples they do it a bit more, but they don't do any kind of the normal ablation. Well, they did it here, but they didn't do it here, so we don't know if this is exactly the what's happening. But let's believe them, I guess. This feels like a complicated thing where they're just saying that normally it's not just a single query key interaction, but there's multiple interactions that contribute together. Um, because, for instance, here you have features that are like the name of aunt feature is both active on Mary and Sue, and so you have multiple interactions. I don't know if this is that relevant. This is kind of more, um, let's say, level 2 of doing the same thing, but now you need to take into account the fact that you have multiple of these possible interactions. So an interesting thing that they're showing by this graph, if I'm understanding correctly, is that basically these, if you were only doing feature attribution, you will only be able to see that this feature that's active on ant is active here, and that it contributes to this feature, name of aunt and uncle. But you wouldn't be able to see why why this head is active. And that's what they're showing here at the bottom, is that this head is active because um, this head activates if there's a title, a feature title, and a first name feature. If there's a feature about titles and a feature about names, and one is in the queries and one is in the keys, it activates this add that then moves from ant to name of ant features. And I guess this was the same thing here, where basically this feature, if you're just doing normal attribution graphs, you'd see this feature that is active on word Sally, and then this feature here that's active and that says Sally, but you wouldn't know why this ad is active, and this ad is active because here there's a feature called that activates on ants, and here there's a feature that activates on names of ants, and so that activates this induction ad that ends up copying this information, which, yeah, clearly gives us more information than what we had um, before. I don't know why this is in French instead of in English, because it would be the same in English, right? The opposite of small is, you could have done this in English. I don't know why they did it in French. Um, but here, so this is the graph that they would get without any kind of um, attention contribution. So they would have features that activate on the word opposite, and maybe they activate also on antonyms. They have features that activate on the word small. Then magically, a new feature that activates on the word large appears. Um, and then this feature that says say large, and then the model outputs grunts. But it's not obvious how this transition between a feature that activates on small to a feature that activates on large happens, and they hypothesize that there's this interaction here that is not captured by the normal attribution graph. Um, and in fact, what they see uh, is that they find uh, key side features, which again are this side, right? Yeah, that are active um, on a certain X thing in the phrases where there's the opposite of X, and are also active on adjectives, while on the query side they're active on opposites and antonyms. And so you see here these features are all say like opposite of, opposite way, and then they're active on a bunch of things. And these queries are active on like antonyms, opposites, and so these keys interact with these queries to make the attention pattern. Yeah, so this is what that they show happens, or they think happens, that you have this opposite feature. This opposite feature uh, basically interacts with this is opposite of feature that acts as a key to this feature that activates on opposite in context. So these two features are basically the same, come from the same origin of seeing opposites. They make this opposite head activate that now connects small to large to then say large. And this transition here um, from small to large was not clear before because there was like no link between this and this, I guess. Or maybe there was and they're just saying that we don't know exactly what the interaction is. But here they show that there's these opposite heads that just flip the meaning of something. And if they don't activate this key, this opposite head will not turn on, and so the model would just do kind of an induction where it sees this open bracket, open thing, and says petite instead of grand, which is this thing that they're showing here. Even though, yeah, it basically just says 50-50. It's kind of unsure if it should say, well, this is not 50-50 because this is log scale, but yeah, it inverts the probability of saying empathy. And then for some reason, other adjectives appear as well. I guess because this disturbance on this circuit brings other information from other parts, because some of these features were active on also just a bunch of adjectives. Yeah, I don't know if I kind of don't think I want to. Maybe let's do one more. Unless let's have a break here and see if there's like if people have specific questions. that they would like to ask or comments about these results?
I think so far for me, this is making sense at like a high level.
Yeah.
Yeah.
Yeah, actually, I don't know. I was kind of expecting that they add interactive stuff so that we could play with them. Um, but I was also not expecting to dive much deeper into like specifics because yeah I just didn't have time to read it into with that much detail. So let's look at the multiple choice one and we'll stop here. So here the idea is that they ask Aiku when did World War II end, and they presented three answers, and the correct one is B. And they're trying to see how the how the model knows that it's B. And they're saying that when they did the graph, it basically just went straight the influence went straight from B to B, and basically this didn't tell them any anything about how the model knew that it was B. Um, and so they're saying that they can that their hypothesis is that B is copied to 1945, then that there's a certain correct answer feature that's active on 1945, and then there's the feature at the end that interacts with this a query that activates that um, interacts with this key feature, which would be the correct answer, and that decides to copy it. However, yeah, but this was the hypothesis, but the attribution graph at the time without attention could not really test this hypothesis. Um, but now what they see is that on the query side, they have features that activate uh, on the bias term that activate on giving an answer. So you see here response and then an answer. The answer is answer, um, and also I don't understand this feature. Okay, something else. Okay. Um, so they have these features that say answers, and then on the key side, um, this feature is only active on the correct answer. So they basically they collected activations on a bunch of answers, and then they see that this feature is active only on the correct answer. But they also have features that activate on false statements, like the bathroom is for eating, uh, which are also interacting negatively with this feature of, say, a multiple choice answer, which basically means that the model is at the same time trying to say the correct answer and try to not say the incorrect answer. And and so yeah, the graph before goes into a more complicated one where the the token A goes this is I don't know what this is, but the token A goes to the correct answer to the correct answer ad, but because the false statement feature is active, this ad is um, neutralized, is inhibited, um, and the same happens with the C, which is also the incorrect answer. But um, the on the C on the B case, which was the correct answer, uh, it it activates the Q keys KQ circuit, which ends up activating the correct answer head, which then makes the model say B. I wish that we were able to see these actual circuits and look at the features, because like we have to put a lot of trust into this plot, because we don't know exactly, we don't see anything. But let's say that is the true case. I wonder what these question marks here mean. I guess that there's the features that mostly activate this false statement and incorrect answers are probably not easy to interpret, and so they're not able to label them. I guess that's why they have question marks. Um, so yeah, this is what I said, and then they validate this by doing interventions. So if they activate the correct answer feature on the path that activates the correct answer on A, and decrease the correct answer feature on the path that goes through B, the model says A. Uh, Interestingly, say if they just shut down B, the model also says A. But you can just, if you just kill B and then make the C circuit stronger, the model says C. So here it looks like it kind of defaults to A at a certain strength, and then instead of saying C, but if you activate the correct answer feature in on the C part of the circuit, the model uh, says C. So this still, yeah, this still doesn't tell us how the model knows how the correct feature are are, are computed in the first place, which is kind of what they're trying saying here with this question marks. But on 1945, which is the correct answer, but mostly on contexts where World War II is mentioned, and also end of World War II. Um, but they say that the errors are too big to actually do any kind of, let's say, final conclusion. Um, yeah, I think this was. I think we're going to stop here, um, unless people have like specific questions about something else below. But it's getting. We can. Sorry, we can look at future work and related work, I guess, because maybe people are interested in that. Um, Important threads were identified based on the manual analysis. Yeah. So in this case, in this other work, they kind of knew already which were the important heads, because they used the heads that automatic circuit discovery found for the IOI task, and so they didn't have to follow all the paths. Um, oh, sorry, this is not important. Um, okay, this is just other people doing stuff. Yeah, and here, instead of doing these attribution graphs, they say that other people did QK circuits by doing um, uh, patching experiments, which is a different kind of way to make circuit attention circuits. And I think this is probably the important bit for people that maybe want to help out. Um, so some future work could be understanding how this attribution can be distilled or simplified, because you get these matrices these matrices for each token for each key query key um, position, but you need to reason about them. Um, yeah, then this second thing that we mentioned, that we get the scores from KQ attribution, but the patterns require the softmax, which makes some competition. Uh, so it's important. Uh, Sometimes it's important to know not only why it attended to a position, but why it didn't attend to a certain position. Uh, but it's unclear how to identify the most important negative contributions. Uh, how can we do this when we have long contexts, because attention scales quadratically, and so to keep to decide which edges to keep becomes very important. Um, then this is a thing about if you have the KQ attributions, is the OV circuit, so the circuit that decides what they add, right? Is it always doing the same algorithm, or are ads polysemantic, where they can have some kind of KQ behavior but different OV behavior? Um, this is also a question related to why the ads attend to certain tokens. So in the case of when an edge has multiple ads that contribute to the edge, do the ads do the same kind of work, or do they do a different kind of work? And then yeah, they kind of open a call out to ask people to extend the open source attribution repo, um, to add attention attributions, but unfortunately, yeah, you'll have to kind of figure out how to do it just from this explanation here, which doesn't seem impossible, but is probably a lot of work to do by yourself. Um, and I think that's it. I know that I heard already some people leaving, but yeah, I'll open again the the floor to questions. Okay, I guess I was clear enough that nobody has questions, or um, I'm going to end it here. Um,